Alright, wrapping up our Intro to Circuits for People Who Are Not Electrical Engineers series, at least for now, we are going to have a crash course on digital logic and logic gates. And this is something that really you could take an entire class or do another entire separate video series on. So again, this is just going to be kind of a one video overview of the topic where pretty much everything we have talked about so far in this video series has been analog, meaning if you make a graph of voltage versus time, you can have a continuously variable voltage that can take on any value between some minimum and maximum, whereas digital voltages are only ever going to be high or low. There's nothing in between. And what exactly that high voltage is going to depend on the system, but common values, for example, are 5.0 volts or 3.3 volts. If you're working with an Arduino, different microcontrollers might have different high logic levels, and then low voltage is usually going to be 0 volts. But I will use the terms high, true, 1 in the binary sense, or refer to a voltage like 5 volts or 3.3 volts, all to sort of mean the same thing, and then they each have their opposite. So opposite of high is low, opposite of true is false, opposite of 1 is 0. Again, in terms of binary numbers, not voltages, this 1 does not necessarily mean 1 volt. And then again, where 5 volts or 3.3 volts are high, 0 volts is going to be low. So each of these pairs kind of means the same thing, and just a heads up in advance, I might sort of bounce back and forth in terms of which one I'm referring to, but remember you can kind of group these together and roughly treat them like synonyms when we're talking about digital voltage and digital logic. Now, if you've taken any sort of programming class, then you are probably familiar with Boolean variables, which can either be true or false. So that's kind of the same thing we're talking about here, except now we're talking about voltages that can either be high or low. And you are also probably familiar with Boolean operators like and, or, and not that operate on these true and false values. For example, independent of programming language, you might know that if you write some statement like if x equals 2, then do stuff, and this part of the code will only execute if x equals 2. But you also might write some statement like if x equals 2 and y equals 3, then do stuff. And because of this and here, this condition here is going to evaluate if this is true, if x equals 2, and if y equals 3, if this is true. But because of the and, it's then going to check if this whole thing is true, and then it will only do this part here if this entire condition is true because of that and. So same concept here, except we are going to do this in hardware instead of code. We are going to have something called a logic gate. There are a bunch of different types and they have different symbols, but this is the symbol for an AND gate. We'll go over these more on the next slide. But that gate is going to have inputs, just like the condition for your if statement here has inputs that can be either high or low, or true or false. And then it's going to have an output that can be high or low, or true or false, depending on the inputs and the type of gate it is. So again, I think for a lot of people who have taken a programming class already, where you're already familiar with this idea, again, I could have put an or there instead of an and then this whole condition would be true if either of these individual conditions was true instead of both of them. So there's a difference between, just like there is a difference between or and in programming, there's going to be a difference between or and logic gates. But again, now instead of doing this with code, we are doing it with a physical circuit and physical voltages that don't require any code to run. Now, we aren't going to get too much into the internals of what is going on in these gates, but one easy way to think about it is using switches. So if I imagine that I have two switches in series like this, connected to then a current limiting resistor with an LED, which we've covered earlier in this video series, and I have a 5 volt supply there. Just assume I've chosen the correct resistor value. We're not going to worry about that too much. I can see that this LED is only going to turn on if both of these switches are closed. So if I call my two switches A and B, and my LED is my output C, then my output C is only going to be high or on if both of my inputs are closed. And say I'm going to call these switches, call that a 0 or low when they're open and a high or a 1 when they're closed. So if the output is only high if both inputs are true, then that is basically acting like an AND function or an AND gate, where in this programming example, the if statement condition is only going to be true if both of the inputs are true. For the logic gate version, the output is going to be high only if both of the inputs are high. And here, the output is going to be high only if both of the switches are closed. So logic gates are doing this with transistors, not with physical mechanical switches like this, but that's another way you can kind of visualize this concept. I could also do that with two switches in parallel, and you may be able to guess already that that is going to give me an OR gate instead, where now I only need one or both of these switches to be closed for the LED to turn on. So if both of the switches are open, or both of my inputs are low, then my output is still going to be low. But if I close just one switch, then that'll give a path for current to flow, my output will be high. Or if I close both switches, then again my output's going to be high. So the two switches in series give me effectively an AND gate, and the two switches in parallel effectively give me an OR gate. Alright, let us now kind of plow through our list of gates. So for each gate, we are going to have four things. We're going to have the name of the gate, the circuit diagram symbol for the gate, the Boolean algebra function for the gate, and what's called a truth table for the gate. And we will explain what that means in a minute. So the first one, wrong color, is just going to be a gate that doesn't actually do anything. So this doesn't really serve a logical purpose. I am drawing a symbol when I want to be writing the name. It doesn't serve a purpose in terms of changing the logic from an algebra standpoint, but can serve a purpose when it comes to buffering, for example, microcontroller inputs and outputs when you want to keep the logic value the same. So just called a buffer. It's going to be this little triangle symbol, not to be confused with an op-amp, where we have input A and output C. And the output is just equal to the input. So again, it is not actually doing a Boolean algebra function or changing anything, but again, you might use this, for example, to protect a fragile microcontroller pin with a buffer so that if something blows up on this end, you maybe just blow up your cheaper logic gate without actually damaging your microcontroller, but no actual logic function. Now, the truth table is going to be a table with a list of the inputs and all possible combinations of the input and the resulting output. So here we only have one input, so our input is either going to be 0 or 1, and then C is just also going to be 0 or 1, the same as the input. So again, not much exciting going on there with the buffer. But next up, we have a NOT gate, which might also be called an inverter, which, as you may guess, is going to invert or change the output. So if the input is true, the output is going to be false, and vice versa. So this looks like the buffer, except we have a little circle there on the output. I have input A, output C. The way we write that in Boolean algebra is C equals not A, or it's just an A with a line over it. And then the truth table is going to look a lot like the truth table for the buffer, except the output is flipped. Now, if the input is 0, the output is 1. And if the input is 1, the output is 0. So again, that is our NOT gate or inverter. Things start to get a little more interesting when we go up to gates with two inputs. So we have our AND gate, which we kind of already looked at on the previous slide. This is going to have the two inputs. It's got this kind of semicircular or dome shape to it. Inputs A and B, output C. The Boolean algebra function, and we're not really talking about actual more complex Boolean algebra operations in this video. That would be a topic for another video. But is going to be C equals A times B with the dot operator there. So if you think about this mathematically with A and B is 0 and 1, then the output C is only going to be 1 if A and B are both 1. Otherwise, 0 times 1 is 0, 1 times 0 is 0, and 0 times 0 is 0. So that kind of, if you haven't seen these Boolean algebra operations before, you can kind of think of it like that. We are now going to have a bigger truth table where we have two inputs, A and B, and our output C. So now we have to go through every possible combination of inputs and look at the possible outputs. So we're going to have 0, 0, 0, 1, 1, 0, and 1, 1. And again, for an AND gate, our output C is only true if both of the inputs are true. So all of these are going to be zeros initially until both of the inputs are true, and then we have a 1. After our AND gate, we are going to have an OR gate. So OR is going to have a slightly different symbol. You have to be careful not to get these mixed up, so I'm going to draw it kind of exaggerated. It's this kind of curvy arrow-looking shape, where again I've got that curved edge over on the left as opposed to the straight edge for the AND gate, and then the right edge is pointy. But again, be careful if your handwriting's getting messy not to get these two symbols mixed up. Where again, I have inputs A and B, output C. The function for this is going to be C equals A plus B. So when I'm talking about Boolean algebra, that means OR, not literal addition. And again, if you kind of think about this loosely in zeros or ones, okay, 0 plus 0 is still going to be 0. 0 plus 1 or 1 plus 0 are both going to be 1. 1 plus 1 is 2, but if you think about anything other than 0 as true, then that still sort of works. Again, we're not totally getting into the Boolean algebra in this video. I should have left myself a little more space for the truth table, but we're going to cram this into the bottom right corner here, where again we have all possible combinations of inputs for A and B, and the corresponding output C. In this case, C is going to be true if either or both of the inputs are high. So C is only going to be 0 when A and B are both 0, and then otherwise the output is going to be true. So there we have our 4 basic or first gates. We got the buffer, the inverter, the AND gate, and the OR gate, but we are going to cover even more on the next slide. So we just talked about OR being true if one or both of the inputs are true. We also have XOR, which is short for exclusive OR, which, as you may be able to guess, is only going to be true if one of the inputs is true but not both. So the symbol for that is similar to the OR gate, but we kind of got that extra little curvy line on the left there, where again we're going to have inputs A and B, output C. The function for this is kind of a plus sign with a circle around it, so that means exclusive OR. And then the truth table, inputs A, B, output C, 0, 0, 0, 1, 1, 0, 1, 1. Again, is only going to be high if one but not both of the inputs are true, so it looks like that. Next up, we have the NAND, or not AND gate, which is basically going to be inverting the output of an AND gate. So our symbol, we have the AND symbol, but then the little circle there on the end. Again, inputs A and B, output C. Function for this one is going to be C equals A and B, but then the not of the whole thing. So the truth table for this one is kind of going to have the output, or the opposite of the AND gate for the output here. So whereas the output of the AND gate would have been 0, 0, 0, 1 here, instead I'm going to have 1, 1, 1, 0. So this is true for every combination except both of the inputs being true, in which case the output is false. We've got 2 more here, both variations of the OR gate. So we have a NOR gate, which is only going to be true if neither of the inputs are true. So kind of like the NAND, this looks like it is inverting the output of an OR gate. So we have the OR gate symbol with the little circle there on the output. The symbol for this, or sorry, the function for this is going to be C equals A or B with a not over the whole thing. Truth table, A, B, C, 0, 0, 0, 1, 1, 0, 1, 1, is only going to be true if neither of the inputs is true. So it's going to be 1 if they're both 0, and then otherwise all of the outputs are going to be low. Finally, we have the XNOR gate, so the exclusive OR version of NOR. Symbol for this one is going to be that XOR symbol with the extra little curvy line. Output over here. Oh, sorry, and I forgot the little circle on the output for that one. inputs A and B, function C equals A, and a plus with the circle around it, B, but then the not of the entire thing. And then the truth table is going to be the not of the XOR gate. So we have 0, 0, 0, 1, 1, 0, 1, 1. And then we are going to be basically taking the opposite of the output here. So this is going to be true if neither input is true, if both inputs are true, but otherwise if just one of the inputs is true, it's going to be false. So there you go. Between these two slides, we have 8 different logic gates, each of which have a different resulting truth table. So for example, if you are designing a circuit with buttons and switches, or you have some digital sensors and you only want your output to be true based on some combination of the inputs, you can select which gate is appropriate. You can also build more complicated circuits using combinations of multiple gates. We're not going to go too far into that in this video, but we will go through one simple example of, say, if you wanted to build a circuit to turn on an LED, only if a certain combination of buttons are pushed. So we showed earlier in the video how you could do that just by hardwiring buttons or switches in series with or parallel with an LED to represent AND or OR gates, but say you wanted to do that with an actual AND logic gate where the output is going to be connected to an LED with a current limiting resistor. We're not worrying about calculating current limiting resistor values in this series. That's covered in in this video that is covered in other videos in this series. Something I haven't mentioned yet is that these gates do usually require their own separate power supply. So for example, 5 volts and ground to the gate itself. And we have our output C here. And again, we want this LED to turn on when the output is high, and I'm using an AND gate because I only want that to happen if both buttons are pressed. So I could wire buttons to my 2 inputs here, where I am going to have push buttons connected up to 5 volts. Okay, so the input will go high when I push those buttons, but I think I covered this in an earlier video somewhere in the series. I'm also going to need pull-down resistors so the inputs are not floating when the buttons are not pushed. So I have a pull-down resistor to ground. So when the button is not pushed, the input is going to be 0 volts. When I push the button, that connects the input up to 5 volts, and the input's going to go high. So with this circuit here, if neither button is pushed, both inputs are 0. Remember from our truth table for the AND gate, the output's going to be low. If I push one of the buttons, then one of the inputs goes high, but for an AND gate, I need both of the inputs to go high for the output to go high, so the LED will not turn on if I push just one button, but if I press both buttons simultaneously, then both inputs are going to go high, the output will go high, and the LED will turn on. If I only wanted the LED to turn on, if I pressed just one of the buttons or both of them, I could replace this with an OR gate or some other combination based on these different gates, depending on, again, what conditions I want for the LED to turn on. I could select a different gate. Another motivation for doing this, say maybe you have some Arduino project and you are building an alarm system. So here's your Arduino, and here are a bunch of different passive infrared or PIR sensors that each have a digital output that goes high when they connect motion. But you just want to turn on some lights and sound a buzzer if any of the PIR sensors detect motion. Well, you could wire each one of these to its own Arduino pin, but if you just want to set off the alarm no matter what, and maybe you have a bunch of other stuff connected to your Arduino and you're running out of pins, you could combine these sensor inputs into OR gates, and then, for example, if I combine 2 of them into an OR gate, then the output of that gate is going to go high if either of these sensors detects motion. Same thing here. If I combine these 2, then the output of that one's going to go high, and then I could combine both of those into a second gate where, again, now if any of these 4 go high, it's going to turn the output of the first gate high, which is then going to turn the output of this gate high, and then ultimately I only need a single Arduino pin. And rather than using 3 separate gates for that, you can also buy integrated circuits that have multi-input gates. So for example, an OR gate with 4 inputs, where you're then going to have a much bigger truth table. I'm not going to bother drawing the whole thing out here, but say inputs A, B, C, D, and output E, where now the output E is going to go high if any of these inputs are high, and you would have the corresponding truth table. When you physically go buy these, they are usually going to come in an integrated circuit package, so you'll need to look up the datasheet for what the pinout of that package is. For example, there's usually going to be a ground connection and a power connection, and then it'll show you, for example, for an AND gate, that these two inputs are wired like that, and then the output is like that. So you have inputs A, B, and output C, but then the integrated circuit is usually going to have more than one, or many times have more than one gate in a single package. So again, depending on which gate you need to go look up what you actually buy, and then look up the pinout of the integrated circuit to figure out how to physically wire it on a breadboard. So again, this video was a crash course in digital logic and logic gates. This is really something you could go take an entire class on, or could do an entire separate video series on, but I am going to stop there for now, at least. So thank you for watching.